Here we're going to talk very briefly on the two very important issues related with numerical resolutions of differential equations. One is the different sources of errors that we are making when using different methods. And the other one is related with the stability, which somehow it's also another kind of error that is also associated with the method, but it's more difficult to appreciate and see it from the method itself. And of course, even though we are going to mention it here, we are going to talk about that a lot later, especially when talking about the finite different methods applied to partial differential equations. So the two different errors that basically errors that we're going to call errors that we are going to consider are first round-off errors that comes that the finite arithmetic precision we are considering for the numbers we are using, the computers. Of course, the numbers don't have infinite precisions. So even though you can increase the precision of the numbers considering double precision in MATLAB, the final at the end, you will always have you have to have in mind that you always have a finite precision for the numbers. So this is one source of error, which is going to call round-off error. And another one is related with the truncation error, which comes from the method. If you remember, of course, in the derivation of any finite difference results for the different methods, we're using the strategy was basically the same. The basic strategy was basically the same, which was using the Taylor expansion. And we're cutting that Taylor expansion at some specific order on the time step, considering that time is the independent variable we are going to consider for the over first order differential equation. So you're cutting the Taylor expansion that was defining the order of the error in the time step. So you are making the truncation in the Taylor expansion. So associated that truncation in the Taylor expansion, that all the methods have an error on the time step. And another kind of error that we're going to separate from the other is what's called stability. It's going to be very important, and sometimes it's not easy to see that directly from just looking at the method. You have to analyze it more in more detail in order to be able to distinguish if your method itself is stable or not. But we're going to talk about that later. But in general, we can say that it's important to have in mind that the numerical dynamics we are going to consider whenever we are considering our first order or second order differential equations, or high order differential equations, of course, are a very pernicious problem. What does it mean? That we are using different effects, like the effects of the integration method, the numerical method you're using for the integration, the time step, the computer arithmetic, etc., can mess the system with the system's behavior in ways that look exactly like real effects. It means that sometimes you're getting some results and actually you don't know if the results you're getting is actually real, or you're getting that it's getting some strange effect which is associated with something which is going wrong with the method. So in order to check that, that's important what's writing here, in order to be sure somehow that the results you're getting and somehow real effect, as we are writing here, you should always distract, at least a priori at the beginning, you should always distract your results and do some basic belief checks on them. What does it mean to do belief checks on them? Basically means that change something and see if the results are still there. If you're getting the same or very similar results, just changing something on the previous approximation. I mean, change, for example, a time step, or use a different method, or use double precision arithmetic instead of single one, etc. And see if your results change. I mean, if your result change, it's not good. It means that probably what you're getting is not something which can be considered real, but some artifact associated, some strange artifact associated to some of the errors that we are making here. And sometimes it might be related with the stability. So it's important to check that. And if they don't check it, actually, if you have that the results are converging, even though you're changing some of the parameters here, it's good. It probably means that you're safer. Now you're safer to trust on the result you're getting. So that's important to do. That's easy and important to do to be at least more sure on the results that you're getting.